Look at this small shiny cube sitting on the table. It is only about 1 inch on each side. It looks like a plain piece of metal, nothing special. But pick it up, and you feel something strange. It is very heavy. Much heavier than it should be for something so small. This is a cube made of tungsten. Blacksmiths, men who work with fire and heavy hammers, have looked at cubes like this many times. For years they have tried to heat it red hot and hit it with their strongest tools to change its shape. Every single time, the cube refuses. It stays hard. It does not bend. It does not soften. Sometimes pieces break off, but the cube itself wins. Now, watch what happens when one blacksmith decides to try anyway. He lights his forge, heats the fire as hot as he can, and brings down his hammer. Will the old ways of metalworking finally beat this metal? Or will the tiny cube teach him a lesson he never forgets? The story of tungsten begins long ago, but the real test comes right now. Long before anyone knew what tungsten really was, people found strange heavy rocks in mines. Back in the 1500s, tin miners in the mountains of Germany saw a dark mineral mixed with their tin ore. This mineral made smelting hard. It seemed to eat the tin like a wolf eats sheep. So they called it wolfram, from words meaning wolf dirt or wolf foam. Miners hated it because it ruined their work. Then, in the 1700s, scientists started looking closer. In Sweden around 1750, a heavy mineral was found in an iron mine. A man named Axel Fredrik Kronstedt called it Tungsten, Swedish for heavy stone. He thought it held a new hidden element that in 1781, the Swedish chemist Carl Wilhelm Scheele did experiments. He took a mineral called scheelite and made a white acid from it. He named the acid tungstic acid. Scheele showed this acid came from something new, but he could not turn it into pure metal. 2 years later, in 1783, two Spanish brothers, Juan José Elhuya and Fausto Elhuya, worked in Spain. They took wolframite, the same mineral miners disliked. They found the same tungstic acid in it. Then, using charcoal and high heat, they reduced the acid and made the first tiny bits of pure tungsten metal. They called it wolfram. This was the real discovery of the element. At first, no one knew what to do with it. The metal was too hard to melt or shape with normal fires. It stayed a mystery for many years, a heavy, stubborn metal waiting for the right time. Now we know how tungsten was found long ago. But what makes this metal so different from others? Why does it fight against every hammer and fire? First, tungsten has the highest melting point of any metal. It takes 3,422 degrees Celsius to melt it, that's over 6,000 degrees Fahrenheit. Normal steel melts around 1,400 to 1,500 degrees Celsius. A blacksmith's forge usually reaches only about 1,000 to 1,200 degrees. So the fire is never hot enough to make tungsten soft like clay. It stays hard, no matter how hot the flames get. Second, tungsten is very dense and heavy. One small cube, just 1 inch on each side, weighs almost as much as a heavy mobile phone or a small hammer. Compare it to steel. Tungsten is almost 2.5 times heavier for the same size. That's why the tiny cube feels so surprising when you lift it. Third, tungsten is extremely hard. It can scratch many other metals easily. But here's the tricky part, it is also brittle. That means when you hit it hard, it does not bend or stretch like steel. Instead, it cracks or breaks like a piece of glass. Steel gets soft and shapes when hot. Tungsten? It stays stiff and snaps under strong hits. These things together make tungsten special, super hot proof, super heavy, super hard, but super hard to shape with normal tools. That's why blacksmiths always lose when they try to forge it. The metal was born to resist change. After the first tiny bits of tungsten were made in 1783, people still could not shape it like other metals. Normal melting and hammering did not work because the heat was never enough and the metal cracked too easily. So, over many years, scientists and workers found a different way, a way that does not use liquid metal or heavy hammers. This way is called powder metallurgy, and it is how all pure tungsten cubes and bars are made today. It starts with the same ores from long ago, rocks like wolframite or scheelite. Miners dig them out, crush them into small pieces, and use chemicals to clean out other stuff. This gives a yellow powder called tungsten oxide, or sometimes blue oxide. Next comes the key step, turning the oxide into pure tungsten powder. They put the oxide in a hot furnace and add hydrogen gas. The hydrogen takes away the oxygen, leaving behind fine gray tungsten powder. This powder is very pure and looks like tiny metal dust. Now the powder gets shaped. Workers press it hard into a mold, like squeezing sand to make a strong castle. For a cube, they use a cube-shaped mold and push with great pressure. This makes a green body, a firm shape that still feels a bit soft and powdery. The last big step is sintering. They heat this green cube in a special furnace with hydrogen, but not hot enough to melt it fully, around 2000 to 2500 degrees Celsius, way hotter than any blacksmith forge. The tiny powder particles stick together and grow closer, making the whole thing solid and dense. No melting, no hammering, just heat and pressure bonding the powder into one strong piece. This is why tungsten cubes look perfect and stay hard forever. The method was born because the old forging ways could never win against tungsten's nature. Normal blacksmiths use fire and hits. Tungsten needs powder, pressure, and very special heat. That's the secret behind the tiny cube that refuses to change. The forge is ready. The blacksmith has worked with iron, steel, and copper for many years. He has shaped horseshoes, knives, and tools with fire and hammer. Now he places the small tungsten cube on the anvil. It sits there, cold and shiny, refusing to look impressed. He starts the fire. Coal burns bright, and he pumps the bellows until the flames turn white hot. The temperature climbs, maybe 1100 or 1200 degrees Celsius. The cube glows a dull red after a long wait, but it never softens like other metals do. The blacksmith watches closely. It should be ready now, he thinks. He lifts his heavy hammer. The first strike rings out loud, clang. The hammer bounces back. No dent appears on the cube. A tiny spark flies, but the surface stays smooth. He hits again, harder this time. Clang, clang. Still nothing. The cube does not move. It does not bend. Small chips of metal sometimes break off and fall to the floor like broken glass, but the main shape stays perfect. He heats it longer. The forge roars. Sweat runs down his face. Now he swings with all his strength. The hammer strikes true, but this time the head of the hammer flattens a little against the cube. A crack appears on the hammer face. The cube? It has one small flat spot from the force, but mostly it looks the same. More hits follow. Each one makes the anvil shake. The cube gets hotter, but it fights back. Tiny cracks form on its edges now, not from bending, but from the shock of the blows. The blacksmith stops. He lowers the hammer and stares at the cube. His breathing is heavy. The tool that never failed him before now shows damage. The cube sits there, still mostly unchanged, still heavy, still hard. It has won again. The old ways of fire and hammer meet something they cannot conquer. The lesson is clear without words. Some metals are not meant to be shaped this way. The blacksmith tried his best. He used the hottest fire he could make and the strongest hammer he owned. But the tungsten cube stayed almost the same. Why did it win so easily? The first reason is the melting point. Tungsten needs over 3400 degrees Celsius to melt and become soft enough to shape. The blacksmith's forge only reaches about 1200 degrees at best. Without enough heat, the metal never gets soft like hot steel or iron. It stays hard inside, no matter how long it sits in the flames. The second reason is brittleness. Tungsten is very hard, but that hardness makes it brittle too. When the hammer hits, the force cannot spread out and bend the metal. Instead, the energy makes tiny cracks start. Each hit adds more stress, and pieces break off like glass instead of flowing into a new shape. The third reason is how tungsten is made. It comes from pressed powder that bonds together under special heat, not from melted liquid metal poured into molds like most tools. Forging tries to force change on something that was never built to change that way. In the end, fire and hammer are tools for metals that soften and bend. Tungsten is different. Its nature says no to the old ways. The cube did not fail the blacksmith. The blacksmith's tools failed the cube. The story of tungsten began in old mines with heavy rocks no one wanted. It grew into a metal discovered by curious scientists, then shaped by special powder methods because fire and hammer could never control it. In the end, when the blacksmith tried his strongest skills, the small cube stood firm. It taught a clear lesson: some things in nature are made to resist change. But tungsten is not useless because it is hard to forge. Its strength makes it valuable. We use it in drill bits that cut through rock, in light bulb filaments that glow for years without melting, in rocket nozzles that face extreme heat, and even in tools that shape other metals. The tiny cube that defeated the hammer is proof of tungsten's power. So when a blacksmith tries to forge a tungsten cube and instantly regrets it, he learns what history already knew. Some metals are born to stay as they are, strong, heavy, and unbreakable.